Welcome to the last lesson on derivatives. This is what everything comes down to, related rates. So after today, you'll be able to find related rates and use related rates to solve real-life problems. So after today's lesson, you will understand why we did what we did for the last month and a half with all the derivatives. Everything we've done with derivatives is going to build up to solving these problems. And these problems are actually word problems. But what I'm going to do is I'm just going to start you with a quick little do now. This is from implicit differentiation, a little warm up. Make sure you guys remember what you're doing. All right, so implicitly differentiate that. All right, ready? So, in case you forgot how to implicitly differentiate since yesterday, right here, 4 times 4x to the third is 16x to the third. Negative 7 times 3y squared dy dx. Do not forget to add the d, whatever variable this is, over dx if you're deriving in terms of x. Here, this you need the product rule. Your f is 3x squared, your g is y. 3 times 2x is 6x, and then the derivative of y is dy dx. Okay? F, 3x squared times dy dx plus y times 6x. So it's 3x squared dy dx plus 6xy. Boop, put that right there. Equals 0 plus 12 times 2x is plus 24x. Good? All right, so collect all the dy dx's on the left-hand side. So that means move u, subtract 16x cubed from both sides. U stay, move u, subtract 6xy from both sides. U stay, because you're already on the right. You're going to collect the dy dx, and you're going to factor it out. So dy dx times 3x squared minus 21 y squared equals, this stays the same. Divide by whatever is connected to the dy dx, and there's your answer. Negative 16x cubed plus 24x minus 6xy over 3x squared minus 21y squared. All right, so you may say, what are we doing that for? Just to warm up, because now we're getting into our related rates, okay? Just want to give you a little bit of warm up. So, you ready? That's easy compared to what we're about to do. So right away you see words, you see pictures, you go, oh no, but it's really not that bad. So I'm going to start by just explaining everything to you, and then after I explain it to you, we're going to build into how to solve these problems. So we're going to start easy, and then we're going to end up very difficult. So original equation, this is probably, honestly, the section that most students struggle with in any type of calculus, okay? The hardest one you guys will take probably all year, but if you do good on it, it means everything else will be easy, right? Good. All right, so original equation, volume is pi over 3 r squared h. That's the equation for what? Volume of a cone. Okay, so here's our cone, and you can differentiate implicitly with respect to t and get the related rate of the equation. Now, what happens here is you have a cone. I don't know if you guys do this, but if you ever used to go to doctor's offices, you used to get little cones and fill them with water. Well, say there's a little hole in the bottom of that water. The radius of the water is shrinking, and so is the height. And you can actually find out one based on the other one, based on a time, based on an equation. Now, why would you do that? You wouldn't. But if you're in the industry, say like a manufacturing industry, you may want to see how quick flows work or stuff like that. Or maybe you're just in the field, you're an engineer, and you want to see how drainage works. So the water cup is just something you can relate to. All right, so you can differentiate. So with respect to t, now what do you think t means? With respect to t is d over dt. T stands for time. So when you're doing related rates impose something over time. So there's always going to be something with time. So when you do rates, you always want to d dt everything. So instead of deriving in terms of x, doing d dx to everything, you're going to derive in terms of t, d dt. Okay? So what are we going to derive in terms of t? We're going to derive the equation. Now, that means we're going to d dt everything. D dt dv, the left-hand side and the right-hand side, just like we just implicitly differentiated. Now, the difference here is there is no t, which is okay. So, do you remember? Think of this one as d dx of y. Our answer is dy dx, right? So what do you think the derivative in terms of t of v, or volume, is? When I point, yell it out. dv dt, right? dv dt. Okay, dt is always going to be on bottom. because it's 1 dv dt, using the chain rule. Now here, r squared h. What rule do you have to use for that? Because we don't know r squared or h. We have to use the product rule. Because r squared and h are two different equations, right? So our f is pi over 3 r squared, and our g is h. What's the derivative of this? Pi over 3 times 2r dr dt, right? So it's pi over 3, 2r dr dt. And you just put the 2 with the pi because constants go together. Derivative of h is, in terms of t, dh dt. Right? Easier than it sounds. So, pi over 3, r squared times dh dt plus h times all this stuff. So when I simplify this, I get pi over 3 r squared dh dt plus 2 pi 3 rh dr dt. And that right there is our equation. Now from this equation, you can see the rate of change of V, so volume changes in terms of time, is related to both how the height is changing and how the radius is changing. Okay, now, in a problem, you'll be given some of these pieces, and then you have to plug them in and solve. But this is just how to pretty much create the equation. All right, so if I knew what the radius is, how fast the radius is changing, how fast the height is changing, I could find the height, or vice versa. I could find out how fast the volume is changing based on the radius, the height, and the other stuff. All right, now, what I'm going to do is, this always helps. What does dv dt actually equal? It's the change in volume over the change in time. Okay, that's what derivatives are, the change of stuff. So what does it actually equal? How fast the volume is decreasing, in this case. How fast is the volume going down? R stands for radius. Okay? H is height. These are all things you should know from this equation. What else do we have here? dr dt. What's that? Or dh dt, sorry. dh dt. The change in height over the change in time. So dh dt actually equals how fast the height is, what? Decreasing. Okay, so how fast the height is going down. Because as the water comes out, the height decreases. What do you think dr dt is? Change in radius over change in time. So dr dt equals how fast the radius is shrinking. Okay, or radius is decreasing. So all this stuff is stuff that you'll have to get and plug in here based on word problems. It seems like a lot, but it's really not that bad. All right? Give me a half hour, 40 minutes, and you'll be okay. So number 2 rates that are related. So we're going to go start very simple, all right? And then we're going to build in. I'm going to give you all the pieces abstractly, and then we're going to combine them all together. Suppose x and y are both differentiable functions of t and are related by the following equation. Y equals x squared plus 3. All right? Find dy dt when x equals 1, given that dx dt equals 2 when x equals 1. So, we have a couple things going on here. So first thing, write the original equation. What's the original equation? Write it down. You do. Write it. All right? I gave you time for that. You should have put y equals x squared plus 3. Now I want you to differentiate this with respect to t. Go for it. You can pause. You done? Hopefully. So you're going to d dt both sides. If you didn't do that, pause it. Do it again. Good. So this right here becomes dy dt. Okay, because I'm going to d dt y, d dt x squared, d dt 3. So I'm going to d dt everything. If you like WWF, d dt WWE, more than just the rest of them. All right. So dy dt. D 2x dx dt. So look at the x's are over dt because they're not t's. And then finally, the anything of a number is just 0. Right? So now I got my equation. So I have to substitute. Do I know what dy dt is? No, because that's what we're finding. When x equals 1, so I could take 1 and plug it in for x. When dx dt equals 2, I could plug a 2 in here. X equals 1, dx dt equals 2. Plug it in. 2 times 1 times 2 is 4, and that's your answer. All right? So what you're going to have to do is you're going to have to differentiate equations with respect to t, and then plug stuff in. So that's part of what you're doing. Not all of it, just part. So, made some nice little guidelines here. First one, identify all the given blank and blank to be determined. Well, we're not in class, so I'm just going to tell you. All the given quantities and qualities to be determined. Make a sketch and label the, what do you think? Quantities. All right, so pretty much what you do is you figure out what goes where, you take all the pieces out of the equation or out of the paragraph, and you just write down what all the stuff is. You draw a picture and you label it to see what's going on. You're going to write an equation involving the variables, right? Whose blank are either given or to be determined. Whose rates of change. So you want to know d blank dt equals question mark. That's what you're going to try to find. Use the chain rule to implicitly differentiate both sides of the equation with respect to time t. That's when you take a d dt of a variable that's not time, and it just becomes the actual power rule, and then d, whatever that variable is, over dt. That's how we're using the chain rule. Okay, you can also use product and quotient rules, though. After completing blank, after completing step 3, substitute into the equation all the known values that we made in our little table before for the variables and the rates of change, and then solve for the required rates of change. This is what the book tells you to do. This is confusing a little bit. I broke it down a little bit easier down here. Step 1, you're going to draw a picture and label it. Step 2, you're going to create a chart. All right? This is going to be a chart. It's going to have the equation, it's going to have what's given, and it's going to have what you need to find. Okay? This isn't how the book does it, but I think this way is the easiest way to explain this stuff. Step 3, you're going to derive the equation in terms of t. Step 4, you're going to plug in all the given variables and you're going to solve. It's like Cliff Notes. This is all this stuff. All right, ready to see how this is applied? Well, let's set this up. Now, this is step 1, finding the stuff. The velocity of a car after traveling 1 hour is 50 miles per hour. I always hated this slide, but it's effective. So, what is our x, what is our dx dt, and what is our t? Our x is traveling. You're traveling. So that's the distance traveled. What's dx dt? Something over time. So that's a rate. So that's something per something. 50 miles per hour. How fast your distance changes as opposed to just the time. Miles is distance, per is your fraction bar, and hour is your time. What's the time? 1 hour. All right, do number 4. Water is being pumped into a swimming pool at the rate of 10 cubic meters per hour. What's V? Water is being pumped into a swimming pool, so V stands for volume, the volume of water. dV dt. That's the volume changing over time changing. So that is a rate, 10 cubic meters per hour. Right? Miles per hour. Number 5 we're not really going to do, but just showing you how we can deal this with rates of revolution. Gears revolving at a rate of 25 revolutions per minute. 1 revolution is 2 pi radians. So, a gear is revolving. This is theta, that stands for angle, so that's your angle of revolution. D theta dt. Well, 25 revolutions per minute isn't an angle, but we can use this conversion to get it into an angle. So you have 25 times, so 1 revolution is 2 pi radians, so 25 times 2 pi radian per minute, 25 times 2 is 50 radians per minute. All right. All right, take a breath. I'm taking a breath. Ready to go? Here we go. Ripples in a pond. I'm going to start you with the easiest problem. This is one I like the most because it's nice and cut and dry. And it has a pretty little ripples in a pond picture here. A pebble is dropped into a calm pond. The ripples form a concentric circle. The radius r of the outer ripple, the ripple on the outside, is increasing, so it's going out at a rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? Now, if you just read that, and all you heard in your brain as I was reading this here was, and you still have no clue what it means, that's okay. What I'm going to do is show you how to break down the parts and solve this. It's all about just picking things out. If you could do that, the hardest part is to take stuff from real life, from a sentence, from a paragraph, and put it into mathematical terms. You could do the math, but getting it to the place where you have to do the math from is where the problem ensues and lies. So let's look. What equation do you think, read this, what equation do you see? So let's look at this. Pebbles drop, become pond. There's no equation for pond. Ripples form a circle. Oh, okay. Something dealing with a circle, right? Radius out of ripple increasing at a rate of 1 foot per second. The radius is 4 feet. What rate is the total area? Oh, look at that. So what do you think the equation could be? I see the word circle. I see the word area. So it'd probably be the, you got it, area of a circle. Now, I don't see that equation anywhere. Well, you have to find out what it is. What's the area of a circle? If you don't know this in calculus, shame on you. But it is pi r squared. If you don't know it, you can look it up. That's what computers are for. That's what your phone is for. So area is pi r squared. Okay, now I got my equation. Good. Let's see. What am I given here? Pebbles, pond. That doesn't help me. So I'm looking for things involving area, involving radius. So let's go radius of the outer ripple is increasing at a rate of 1 foot per second. Now, here's the key. Increasing in your mind should trigger the word what? Rate. Rate. Per second, per time unit. So anytime you see that, it's something dt. Now, since the radius is increasing, it's dr dt is 1 foot per second. Okay, so you got radius, increasing, rate. That means dt. Per second, dt. So 1 foot per second. All right? Now, when the radius is 4 feet, what does that mean? R equals 4. Now, would I just plug in 4 right away? I get, okay, area equals pi times 4 squared, area is 16 pi. No, that just tells us what the area is at that time. But what we're trying to find is, there's a question that tells you, that signals question for you, what rate, okay, so rate means something over dt, is the total area changing. Changing is dt as well. So dA dt. Now if we just plug the 4 in here, we get area is 16 pi, and that doesn't help us because there's no dA dt there. So because we need to know when the radius is 4 feet, what's this changing at? We don't plug in the 4 feet until we have the related rate equation. So we're going to have to do what to that equation? So step 1, have your picture, set up your stuff, right? Step 2, I forget that was filling your chart, right? Step 3, we derive your equation, right? So we're going to derive both sides in terms of t. What is d dt of a? dA dt. d dt of pi r squared. Pi is a constant. So it would be pi times derivative of 2r, or r squared is 2r dr dt. So now we have our related rate equation from the equation that we got from the paragraph, right? And now the last step is the plug in and solve. So dA dt, we don't know what that is. 2 pi is a constant. R is 4 and dr dt is 1. This is why making a chart makes everything easy. dA dt equals 2 pi 4 1. 2 times 4 times 1 is 8 pi feet per second. All right? If you did it regularly and did whatever the number is, what's 8 pi? Like 21, 20, I don't know, 25.2 or something like that. Somewhere around there, 24 point, yeah, I don't know. Good? All right, 25.1. Ready for next one? We'll go easier. Find the rate of change of the distance between an origin and a moving point on the graph. Y equals x squared plus 1 if dx dt equals 2 centimeters per second. So what's the equation? Never going to be this easy, but this was your do now, that's why I made it easy. dx dt given to you. So what do we have to do this equation? Derive it in terms of t. So we're looking for dy dt, rate of change, the distance between the origin and moving point changing. So d dt of y equals d dt of x squared plus 1. Derivative of y. 2x dx dt, 0. Let's plug in some stuff. And you don't have to write this a second time. I just changed the colors to make it easier for you guys to see. We don't know what this is, 2x, and we know this is 2. 2x times 2 is 4x. So what happens is the rate of change, the y value changes 4 times whatever the x value is. And that's it. See how easy that is? Ooh, this one's a fun one. I wish I had my board for this one because I can't draw my pictures. Usually I draw the pictures on the board next to this because I don't have enough space on my things. But I'll just tell you what the pictures are. A sand and gravel plant. Sand is falling off a conveyor, all right, onto a conical pile at the rate of 10 feet cubed per minute. The diameter of the base is about 3 times the altitude. At what rate is the height changing when the pile is 15 feet high? So what I want you guys to do is try to fill in that chart real quick. All right, you got it filled in? Let's see how this works. So, what you have here, let me explain some stuff to you. You have I got my board here, a sand and gravel plant. So, what you have pretty much is you have a conveyor belt. You have sand under the conveyor belt. All right, so there's your conveyor belt. My conveyor belt. You have sand going off the conveyor belt, and it's coming down. And what it does is, it makes a pile. That's a cone shape. And this is all sand. Now, as more sand comes, what happens is the cone gets larger. And it gets larger and larger and larger, and then you have a big cone shape. Okay? So, what you want to know is your sand is falling off the conveyor onto a conical pile at the rate of 10 cubic feet per minute, right? So that's how fast the sand's coming off. The diameter of the base is 3 times the altitude. So if I have the base here, altitude is another word for height, right? So whatever the altitude is, the height, the base is 3 times that. This isn't a very good drawing scale. All right, so altitude and height are the same thing. So I got that. At what rate is the height changing when the pile is 15 feet tall? So you're trying to figure out how high. You're looking for how much higher this is getting when it's 15 feet tall. All right, so this is what you should have drawn. Watch me have it in this slide. So the equation, conical pile at a rate of 10 feet per minute. All right, so what's that? Volume. Okay, conical pile, cone, volume of a cone is 1/3 pi r squared h. All right, the diameter of the base is about 3 times the altitude. All right, we went over that. The rate is 10 cubic feet per minute. So that's dV dt is 10 cubic feet. Now here's where you have to get a little tricky. And this is actually harder than the next bunch of problems, but I wanted to throw in a hard one to see where we're going. Where we at? The pile is 15 feet high. So what's that? Altitude or height, right? Altitude, height, same thing. A and H are interchangeable. So now we got all this, but it says the diameter of the base, or what rate, is the height changing. What's that? Rate means d something dt, d h dt. All right, you saw that from my picture. Now, here's the key. Diameter of the base is about 3 times the altitude. So, altitude, the diameter, is 3 times A. Do we know either of those right now? No. But we will know when it's 15 feet. So, A, altitude is the same as height. So, the diameter is 3 times the height. Okay? Right here. They just use synonyms, altitude, height. Now, the diameter is 2 times radius, right? Because we don't want diameter, we want radius. There's no diameter in this equation. Everyone gets that? So that means the radius is half the diameter, or since d equals 3h and d also equals 2r, 2 times the radius equals 3 times the height. Follow me? Radius equals 3h divided by 2. So how does that help us? Well, we're not given anything about the radius or diameter, right? But what we are given is, I could take this 3/2 h and plug it in for r. Now the reason you want to switch out the r, not the h, is you have the h for later on. So you're going to plug the h back in. I have the dv dt, so I'm going to use that. Good. But I don't, and I have dh dt. I don't got dr dt, and I do not have dr dt, and I do not have r. So that's why we're going to have to replace the r with an h right away. So I go into my original equation. Volume equals 1/3 pi r squared h. And I replace that r with a 3/2 h. Okay, this problem is meant to make your brain explode. But some people get it. 1/3 pi, 3/2 h squared. 3 squared is 9, 2 squared is 4, h squared is h squared. 1/3, 1 times 9 is 9, 3 times 4 is 12 pi, so it's 9 over 12, which reduces to 3/4, right? Pi, h to the 3 plus 1 is 3rd power. So I was able to rewrite our equation as this, based on this one little simple fact, that diameter is 3 times the altitude. All right? Got it? Okay, so what do we do now? You got all this. The setup is the hard part. You derive that in terms of t. d dt of v equals d dt of 3/4 pi h cubed. Derivative of volume is dv dt. 3/2 pi 3h squared dh dt. And now, 3 times 3 is 9/4 pi h squared dh dt. This just was 3 times 4. What I'm going to do next is I'm going to take this and I can plug everything in. dv dt is 10. 9 over 4 pi h is 15 squared dh dt. You can't prematurely throw h in there. You don't throw it in until after you derive. 10 equals 9 over 4 pi. 9 over 4 times 15 squared. 9 over 4 times 225. 225 times 9 divided by 4 times pi is 1,590.4. 10 divided by that number is 0.0063 feet per minute. Right? Or 6.3 times 10 to the negative 123. Right. Once again, I don't want to waste my beautiful picture. Hopefully this is zoomed nicely. And that's what we did. I don't know if that works or not. This is going to be my board, these little things. All right, the radius r of a circle is increasing at the rate of 4 centimeters per minute. Find the rates of change of the area when. So this is pretty easy. So why don't you try to solve this one? Good? So you have a circle. The radius increasing at the rate of 4 centimeters per minute. So what does that mean? What is that? Find the rate of change of the area when. Radius is 8, radius is 32. So you have area of a circle is pi r squared. You're given it's increasing at a rate of 4 centimeters per minute. So that's what? dr dt. What are you trying to find? The rate of change of the area. So you're looking for dA dt. All right? if you drew a picture, and you don't have to draw the picture, so just to help you, you should have, I'm hoping this is focused, you should have a circle. In the circle, it should say the radius is going outwards, okay? And you're trying to check the... All right, so what do we do the equation? Derive it. d dt of A is dA dt. Pi 2r is 2 pi r dr dt. Now we're going to plug some stuff in. We don't know what dA dt is. We know r is, don't know what it is, dr dt is 4. dA dt equals 8 pi r. Now, whatever the radius is, you multiply it by 8 pi, and that tells you how fast the area is changing. All right? When the radius is 8, you plug 8 in for r. 64 pi centimeters squared per minute. Ah, when the radius is 32, plug it in. dA dt equals 256 pi centimeters squared per minute. What you're doing here is setting up an equation, and you would do it like this, because now you can just plug in any number you want for radius, and you can find out how fast the area is changing. All right? I like this lesson. You guys like this lesson? I like this lesson. It goes a lot quicker than all the ones with all the equations and stuff. All right. We're almost halfway there. Air is being pumped into a spherical balloon at the rate of 4.5 cubic feet per minute. Find the rate of change when the radius is 2 feet. So how do we do this? Anyone? Anyone? What's the equation we're going to use? So you got a spherical balloon right here. I need to draw a picture. I got my picture there. First thing we should see is spherical balloon. When you hear a three-dimensional figure that represents volume of the sphere, 4/3 pi r cubed. Rate of radius is 2 feet. What's that? R equals 2. Rate of 4.5 cubic feet per minute. What is that? 4.5 cubic feet per minute. Cubic represents third to the third power, which is volume. So it's dV dt equals 4.5 feet cubed per minute. What are you trying to find? The rate of change when the radius is 2. What are you trying to find the rate of change of? Well, not the volume. There's only one thing left to find the rate of change of. The radius. So you're trying to find dr dt. All right? Hopefully you're able to set this up. If you're not, you got some time. d dt of v equals d dt 4/3 pi r cubed. We're going to drive it. You done? dv dt equals 4/3 pi times 3r squared dr dt. 4/3 times 3 is 12 over 3, or 4 pi r squared dr dt. All right, or you can just cancel the 3's. Now, when we plug this back in, we're looking for dr dt. So we plug in dv dt. Even though it's by itself, you can still plug it in. 4 pi times 2 squared dr dt. 2 squared is 4. 4 times 4 is 16 pi. 4.5 equals 16 pi dr dt. Divide both sides by 16 pi. Now, when you divide something by 16 pi, you do 4.5 divided by, open parentheses, 16 pi, close parentheses. If you don't put it in parentheses, it's going to mess up your answer. So you should get 0.0895 feet per minute, and that is your dr dt. Or you can say 8.95 times 10 to the negative 2 feet per minute. All right. If you got this wrong, you probably didn't put your 16 pi in parentheses. Now, here's some key things that I picked up I like to throw in here. If you are dealing with distance, all right, such as feet, inches, meters, miles, centimeters, okay, that's dx dt, okay? X is pretty much just linear distance. If you're dealing with area, you wouldn't be, say we're still dealing with feet, it would be what kind of feet? Square feet, right? Feet times feet is square feet. And it wouldn't be dx dt, it'd be dA dt, capital A. That's how you know you're dealing with area. And then finally, if you're dealing with volume, it wouldn't be feet squared, it would be cubic feet, right? Because it's a dimension times a dimension times a dimension. And you'd represent that with dV dt. Okay, so when you're writing out your equations or what you're finding and not finding, you're going to use these key things and these key things in order to figure out what you need to put in here. All right, all your deduction skills are coming around. Water is being pumped into a cylindrical swimming pool with a radius of 12 feet at a rate of 6.2 cubic feet per minute. Find the rate of change of its height when the water is 3.2 feet high. Go. No, that's not my pool. A lot nicer than my pool. All right. Equation. Cylindrical swimming pool. Wait, cylindrical? Is that a 3D model or a 2D model? Cylinder is like a can of soda. This is like a cylinder. 3D. So, volume of a cylinder. Anytime you're dealing with 3D models, is volume. So, what's the volume of a cylinder? Do you remember? Area times the height. So, it's pi r squared, which is the area of a circle, times its height. All right. Radius of 12 feet. So, what's that? R equals 12. Rate of 6.2 cubic feet per minute. Cubic feet, we just said when you see feet cubed, that's what? Volume per minute is dt. So dv dt equals 6.2 cubic feet per minute. See? Now you're getting it, right? All right, so find, so this is what we're finding, the rate of change of the height when the water is 3.2 feet high. Oh, so 3.2 feet high, h equals 3.2. Rate of change of the height, dh dt. Now, I hate to do this to you. Look, got this. So pretty much what's going to happen is, this is going to turn into a dv dt, an r and a dr dt, and a dh dt. Are we missing anything here? We don't got a dr dt, right? What do you know about a cylinder? No matter how much water I put in the cylinder, what do we know about this stuff right here? I'll give you a hint. What about the radius of a cylinder? It never what? It never changes, right? Since the radius of a cylinder never changes, I can actually plug this into the original equation before I derive. Can I plug the height in? No, because the more water you put in, the higher the water goes, right? The less water you have, the lower the height goes. So the height can change. The radius of this pool isn't going to ever change. If it does, your pool's collapsing and you're in trouble anyway, so you don't have to worry about water. So since this radius is always constant, I could plug it into that equation. So I got volume equals pi 12 squared h. Volume equals 144 pi h. Okay? Volume is always going to equal that. So depending on what the height is, that changes your volume. Radius never changes. That's why I can do that. So now, I'm going to derive that in terms of t. d dt of v times f. All right, hopefully pause and pause. dv dt equals 144 pi. Derivative of h in terms of t is just dh dt. Now, what do you notice is missing here? The height. I don't got an h to plug in. Does that matter? No, you don't always have to plug in everything that's in here. 6.2 equals 144 pi dh dt. 6.2 divided by open parentheses. All right. Let me go tell you this first. There's no need to input h because dh dt is constant. So what that means is the pool, since the radius is constant and it's just a cylinder, when he's filling it up, or she is filling it up with water, the height is going to rise at the same exact rate no matter what the height is. If the height is 1 foot, if the height is 0 feet, if the height is 5 feet, unless the water starts overflowing out of the pool, and then it's raising 0, the height is always raising at a constant rate. It's always going to be the same. So it doesn't matter what this h is. It's negligible. Negligible. I can't even say the word now. You know what word I'm talking about. So it's not necessary. So 6.2 divided by 144 pi, make sure the 144 pi is in parentheses, and you get 0.0137 feet per minute, or 1.37 times 10 to the negative 2 feet per minute. That's how high it's rising, at 3.2 feet, at 1.7 feet, at 37.8 feet. Nope, not 37 feet. That'd be a tall, tall pool. All right. So now that you guys kind of got your feet wet, right? That's what they say. You're kind of a little bit confident. I'm going to break your confidence. An air traffic controller spots two planes at the same altitude. So this one, it's like you're from space and you're looking down. All right? The two planes are converging as a point as they fly right angles towards each other. So you have this plane down here, this plane here. Okay, they're flying towards each other. Boom, you don't want them to hit. One plane is 225 miles from the point. That's this plane right here. 100, 200, 225. Moving 450 miles an hour. The other plane is 300 miles from this point, moving at 600 miles an hour. Oh, it's going fast. At what rate is the distance between the planes decreasing? This is how radar is used, how they can track planes and stuff like that to make sure they do not collide. All right? What equation do you think we use? Now, what shape do you see there? Here's your hint. Triangle, right? So what equation do you think you use? What's the most famous equation for a triangle? Not the area, not the perimeter, but what do you think? Flies at right angles to each other. The key word is right angles. Right triangles give you our favorite equation. Well, my favorite from when I used to teach geometry. A squared plus B squared is C squared. Pythagorean theorem. Now, what does that have to do with this? Well, let's see. A squared plus B squared equals S squared. I'm going to turn it to an S. Why I turn it to an S? Because I don't know if you can see on your packet, it looks a lot nicer. This is S. The distance between the planes, they say, is related as S. That's just what they call it, so I just turned my C to an S. C is always your hypotenuse. So A and B are interchangeable. So what I'm going to start with is one plane is 225 miles from the point. So I'm going to call that A. So from here to here, I'm going to say is my A, 225. So if that's 225 and it's moving at 450 miles an hour. So moving is a rate. So what do you think that is? What's 450 miles an hour? What dt? It's moving at a rate 450 miles an hour. It's d a dt. Okay? A is the direction. The rate is the direction over the time. All right? The other plane is 300 miles. So what is that? This letter is, what's that? B. So if this is B, now we're moving at 600 miles an hour. 600 miles an hour would be dB dt. All right? At what rate is the distance between the planes decreasing? Now, we have A, we have B. Can we find out what S is? Now, we want to know what S is just. Now, if we change one of these, S is going to change. We could find S when A is 225 and B is 300. How? What do? We plug it into the Pythagorean theorem. A squared, 225 squared, plus 300 squared equals S squared. Square those in your calculator. Add them. You get 140,625. Second x squared, or square root of that, is 375. So when and only when A is 225 and B is 300, S is 375. All right? Now, what are we trying to find? At what rate is the distance between the planes decreasing? Rate distance, d s dt. All right? You're probably going like, whoa, what is going on? Because you found all that, everything else is easy. See, look, I need all the space just to find stuff. So what do I do with this equation? I derive it in terms of t, d dt of a squared plus b squared equals d dt of s squared. Derivative of a squared is 2a dA dt. Derivative of b, 2b dp dt. Derivative of s squared, 2s ds dt. So I got 1, 2, 3, 4, 5, 6 separate variables. Look at this. 1, 2, 3, 4, 5 variables are given, and I'm trying to find the sixth. So I'm trying to find ds dt. I'm going to plug in 225 for A, 450 for dA dt, 300 for B, 600 for dB dt, and then 375 for S. And now it just becomes math. 2 times this, plus 2 times this is 500,000, 600 562,500 equals 750 dsdt. That divided by 750 means this distance is changing at 750 miles an hour. All right? So as they get closer, 750 miles an hour is how fast these are getting closer. All right. Break it down. Get some color pencils. Make things life easier for you. All right, speed of an airplane. I want you to try this on your own. Go. All right, let's see it. Airplane is flying over the same way we just did this. Flying over a path that will take it directly over a radar tracking station. If S is decreasing at a rate of 400 miles an hour when S is 10, what is the speed of the plane? So, key to this equation, Pythagorean theorem. Right triangle, you're given 3 sides. Now, what do you notice about this right triangle? One of the sides is 6 miles. Now, when a plane flies, now this guy's just flying. He's not landing or approaching. So when it flies, does it fly straight or does it fly like just go all the way, like that? No, it flies straight across the sky. So what do we know about the 6 miles? It's always going to be 6 miles in the air, right? So A is 6 miles. B is X, and your C is S. So A is always going to be 6 miles. So I can plug that into the equation right away and say 6 squared equals X squared plus S squared. 36 equals X squared plus S squared. So this is the equation we're going to use because it's always 6 miles in the air. All right? Now, let's see what else we're given. S is 10 miles. S equals 10. We're given a rate of 400 miles an hour. So S is decreasing. So D, S dt, is 400 miles an hour. What is the speed of the plane? Let's see. Wait. What are we going to try to find here? When S is 10, can we find X? We're going to use our Pythagorean theorem. So when this is 10, the way to find X is 6 squared plus B squared. 6 squared plus S squared is 10 squared. 36. Subtract from 164. And X is 8. So only when this is 10 miles away, X happens to be 8 miles away. And now what are we finding? What is the speed of the plane? The speed of the plane is going that way. It's dx dt. Right. Now that we got our formulas and we're set up, we're good to go. Derive this equation. What's the derivative of 36? 0. Derivative of x squared. 2x dx dt. 2s ds dt. Now we're going to plug in some stuff. X is 8. Dx dt we don't know. S is 10. Ds dt is 400. 16 equals 8,000. Dx dt equals 8,000. 8,000 divided by 16 is 500 miles an hour. So the plane is going 500 miles an hour. All right. Whew. That's pretty easy, right? You guys doing good yet? I'm going to apologize in advance. This is the second hardest question. This is the hardest type. This one is a little bit different. Find the rate of change in the angle of elevation of the camera shown below. 10 seconds after liftoff. This is probably the hardest question we're going to do. So, think about it, fill it out, see what you get. All right, so number 1. Ow, that's my knee. SOHCAHTOA. Trig functions. How do we know to use trig here and not a squared, b squared, c squared? That little figure right there, that symbol. That theta right there means we're going to be dealing with an angle. The word angle of elevation means we're dealing with angles. All right, so we have one side, we have a second side, and we have an angle. We don't care about this anymore. So, what trig function do you think we use? If this is the angle, SOHCAHTOA. Opposite, adjacent, hypotenuse. This is opposite and adjacent. So we will be using which one? TOA. TOA means, what's it? Sine opposite over hypotenuse, cosine adjacent over hypotenuse, TOA is tan opposite over adjacent. So our formula is going to be tan opposite over, well, adjacent is always the same. Adjacent is 2,000. Opposite is S. So there's our equation. See, bring it back to geometry. If you're lucky enough to have me, guys like that. We were killed at this stuff. All right, given. Where are we at? What am I doing here? 10 seconds. So what's 10 seconds? T. T equals 10. Now we only have a position function right here. So from that position function, at 10 seconds, can we find out the rest of this? Yeah. We can find out S, right? So S is 50 times T squared. 50 times 10 squared. 50 times 100 is 5,000. So S is 5,000. Now, since S is 5,000, can we find out what theta is? Yeah. So when S is 5,000, because we don't really care about the time, we care about S and theta, we plug it into this equation. 5,000 over 2,000. Now, do you guys remember how to solve these? When you're trying to find the angle and you're given the two sides, you have to use the inverse. All right? So it's tan, inverse tan negative 1 of 5,000 over 2,000, or 5/3, or 5/2. So the way to find tan inverse on the calculator, you just hit second tan, 5 divided by 2, close parentheses. And you should get 68.2. Now, did I put this on here? What are we doing? Nope. Make sure your calculator is in radian. If your calculator isn't in radian, you're going to get some wacky answer, and it's going to be no good. I mean, a lot of times, especially graphing calculators, their default is degrees. You do not want it in degrees. You want it in radian. So go to the mode and change it. Good? All right. So what else can we find here? All right. Rate of change of the angle of elevation says d theta dt. Are you missing anything else? No? All right, so let us derive. We're going to derive this equation right here. The derivative of S. Now, the reason we're deriving this is we need to know what how to find this stuff, right? So, S equals 50t squared. So if we derive that equation, the function, we could find out what ds dt is, because we don't know what ds dt is, right? We're going to need to know it, because we got S, we got theta, we're finding d theta dt, so the only thing we don't have is ds dt. So, in order to find that, simply derive the equation. I told you this is the most difficult one. So ds dt equals, the derivative of this is 50 times 2t. Now, why is there no dt dt? Because this and this match. Since they match, you don't have to worry about that. But now we know ds dt equals 100t, and when t is 10, 100 times 10, ds dt gives us the value now of 1,000. So now you have the 1, 2, 3 things you need, and you know what you're looking for. Told you, they're not always going to be this difficult. None that I'm going to give you after this are going to be this difficult, but it just shows you where they come from. Derive derivative of tan, secant squared. So this is secant squared theta, d theta dt. Derivative of secant is ds dt, so it's 1 over 2,000, that's your constant, ds dt. So now we can plug in some stuff here, right? We don't need to plug in s, because there is no more s. We just use that to find these two things. All right? Secant theta, we know theta is 68.2. D theta dt is what we're looking for, 1 over 2,000 times 1,000. Now, secant squared 68.2, the way you find that is, in your calculator, you hit secant 68.2 equals, right? You take that answer and then you square that answer. All right, because technically it's secant 68.2, and then the whole thing squared. That gives you 7.25. 1,000 divided by 2,000 is 0.5. 0.5 divided by 7 1/4 is 0.069 radian seconds. All right? Got it? And radian seconds is how you change degrees. Wasn't that easy? Like I said before, your calculator wasn't radian. Brain burnt out yet? All right. Let's go back to an easy one like we just did. I want you guys to attempt this problem right here. Oh, this is a do now. So this should be done on Canvas. All right, here we go. An airplane is flying at an altitude of 5 miles and passes directly over a radar antenna. When the plane is 10 miles away, the radar detects that the distance is changing at a rate of 240 miles per hour. What is the speed of the plane? Now, look, do you see angles? No. Do you see a right triangle? Yes. So, what are you going to use? Pythagorean theorem. Now, when using Pythagorean theorem, because we have three sides, aren't any of the sides always going to remain the same? S changes, X is changing, always stays 5 miles in the air, right? Because he's flying here, constant. So, we know that 5, which is our A, you could be your B too, it doesn't matter, is always going to be this, X is always going to be B, and S is always S. So, 5 squared equals X squared, 5 squared plus X squared equals S squared, 25 plus X squared equals S squared. The X's and the S are like tongue twisters. You try to say that much time fast. All right, given. Now let's go look see what else we got. When the plane is 10 miles away, S equals 10. Oh, my little thing got a little bit. 10 miles away. So, what does that mean? 10 miles away. What we got? S equals 10. It says it. Distance is changing at a rate of 240 miles per hour. Changing. S changing. dSdt equals 240 miles an hour. What is the speed of the plane? dx dt. Now, also, since we have S here, we can find out what X is when S is 10, and only when it's 10. A squared, B squared is S squared, 5 squared plus X squared is 10 squared, 25 and 100, square root of 75 is 8.66. So only when this plane is 10 miles away, it's 8 2/3 horizontally away. And like I said before, speed of the plane is dx dt. Sorry, sometimes I forget to do this. I do it later sometimes and earlier sometimes. So. All right, anyway, we're going to derive everything. Derive our equation. 0, 2x dx dt, 2s ds dt. 8.66, we don't know. 10, 240. 17.32. 20 times that is 4,800. Divided, and you get 277.1 miles per hour. That's pretty good for 277 miles an hour. Typically, you want to just go to 3 significant figures. I go all over the place here, just to make sure you guys' calculator's working. All right. Problem 13. Fishing. You like going fishing? Fish is reeled in at the rate of 1 foot per second from a point 10 feet above the water. At what rate is the angle? Ooh, what does the angle mean? Not using Pythagorean theorem, and it's a triangle, so you're using SOHCAHTOA. So, which ones are we using here? Angle, this is opposite, and this is hypotenuse. Opposite hypotenuse is sine. So the equation is sine 10 over x. Right? Now, what else do we got? If you want to rewrite it, because we're going to derive this, sine theta equals 10 x to the negative 1. It's just easier to derive x to the negative 1 than 1 over x. Given. Fish is reeled in at 1 foot per second. What does that mean? Reeled in 1 foot per second. dx dt. This is your fishing reel. Fishing reel, this is your line. Total of 25 feet from the end of the rod to the water. That's your x. Can we find the angle? Yeah. So the way to find the angle here, we have 10 now. We have 25. So sine theta equals opposite 10 over adjacent. So the way to find theta, when x is 25, and only when x is 25, sine negative 1 of 10 over 25, calculate in radian, 23.6. So this angle is 23.6. This angle of elevation is 23.6 when this has 25 feet of line of the water. All right. What are you finding? What rate is the angle of the line and the water changing? Angle changing is d theta dt. All right, so this isn't really that bad. See, it's like using the other one. The other one, I went really maximum difficulty on the other one, just to see. Very challenging for you. Derive sine. Derive tan x and -1. Derivative of sine is cosine. So this becomes cosine theta d theta dt. This becomes 10 times -1 x to the -2 dx dt. All right. Plug in your d theta dt. We don't have one. Plug in your theta, 23.6. Plug in your x, 25. Plug in your 1, dx dt. Cosine this. -10 divided by 25 squared is -0.016. All right. Divide, and you get -0.174 or -1.74 times 10 to the -2 radians per second. So that means that where is it? The fish is reeled in. As you reel this in, this actually shrinks. The angle shrinks. All right. Right? Yeah, the angle goes down. Any questions? I think that's what it means. I could look back, but I'll look back. My brain's starting to get fuzzy again. All right. What do we got? 6 more problems. Airplane flies from an altitude of 5 miles towards a point directly over an observer. The speed of the plane is 600 miles an hour. Find the rates at which the angle of elevation is changing when the angle is 30 degrees. So, angle here. So what kind of equation we're going to use? SOHCAHTOA. Airplane flies from an altitude of 5 miles. So that's opposite. Now what are we looking for? Towards a point directly over an observer. The speed of the plane is 600 miles an hour. So is the plane going towards them or is the plane going across the sky? Going across the sky, right? So that means it's related to the parallel line here, which is down here. So that's opposite over adjacent. Opposite over adjacent is TOA, or tangent of opposite over adjacent. Tangent of 5 over adjacent, or tangent theta equals 5/8 to the -1. See, once you find that out, we're good. Given. All right, let's see some stuff that we're given. Angle is 30. Theta equals 30. Speed of the plane, 600 miles an hour. dA dt equals 600. All right, we need to find A. So we can find A when this is 30. So we're just going to plug the 30 into our tangent equation. Right? Opposite, adjacent. So tan 30 equals 5 over A. Way you solve this is you would multiply both sides by A and divide both sides by tan 30. So A equals kind of like a cross multiplication. 5 divided by tan 30 in radians. And your A is 8.66. Oh, where's that? What are we looking for? Find the rates at which the angle of elevation is changing. That's d theta dt. And now we're ready to go. Derive this equation right here. Hard part becomes easy. Secant squared theta, d theta dt. 5 times -a to the -2 is -5a to the -2, dA dt. Sorry, I forgot to say dA dt. Plug some stuff in. 30, we don't know. 8.66, 600. The reason I change it from this to this is just so you can see what it is. If you just want to raise this to the -2nd power, you can. You get the same answer. When you type secant into a calculator, you have to do 1 divided by cosine 30. It's not cosine -1. Okay, even though it says it's the inverse, it's not technically the inverse. All right, so 1 divided by cosine 30, and then you're going to square that answer. You get 1.33 d theta over dt equals -40. D theta dt equals -30.08 radians per second. That's fast. Right. Any questions? Any questions? No? Right. Now, here, I made this. Here's a quick way. I like this slide. I made this last year in order to solve word problems. First thing you want to do is you write the equation, right? So when you do this, this used to be what I put on the board every year, but I just made sure I transferred it to here so you would have it. There's 3 types of equations you can write. 4 types. Areas. You see the word area. It mentioned a 2D figure like a circle, square, triangle, something like that. You see something squared like feet squared, meters squared, you know it's areas. The second type of word problem is with volumes. That you see the word volume in there. You hear a 3D figure like a cone, a cylinder, a cube, a pool, something like that. You see feet cubed, meters cubed. You see one of the units cubed. All right, so that tells you in your brain volume problem. Then there's the Pythagorean theorem problem. That is a squared plus b squared plus c squared. And you see there's a right triangle, okay? You're creating a right triangle and you're given 2 of the 3 sides and you have to find the third side, or you're given all 3 sides and you have to find one of the rates of one of the sides, okay? Then you have a trigonometric formula. This one's a little trickier. This one deals with SOHCAHTOA. This one, you're given a right triangle and you see that you're trying to find an angle, right? So maybe there's an angle of elevation, maybe you see an angle on the picture, maybe they're asking you how the angle's changing, something like that. That's when you use your trig formulas. So these are the 4, not all, these are the 4 main ones, okay, of rates of change. Now, step 2, so you figure out which one you're going to use there, you write the equation of the stuff you're doing. So second thing you do is do the chart. With the chart, you're given a rate. You have to see if the rate's increasing, decreasing, changing, speed, per second, per minute, per hour. So if any of these words are in the paragraph that we are determining, okay, that stuff goes in your chart, okay? When you see the word rate, increasing, decreasing, changing, speed, per second, per minute, that's something over dt, okay? If it just says the other stuff, it's just by itself, okay? So that's d something over dt. You derive in terms of t. So you d dt both sides, okay? So for instance, if it was a letter, any letter it'd be like dmd over dt, okay? If it was a letter squared, it'd just be whatever that number is times, you derive this using your normal power rule, and that number, that letter over dt, okay? If it has a pi involved, 4 pi r cubed, so the 4 pi is your constant, 3r squared dr dt, so then you multiply them in the end. 3 times 4 is 12 pi r squared dr dt. Okay, so you just derive it normally, and remember pi is a constant, it's not a variable, so you don't have to do any of the rules to it. Last step, you solve. When you solve it, you substitute in the numbers for the known variables, and you solve for the unknowns. If you follow this simple chart, which I used to write on the board every day before class until I figured out, you know what? I'll just put it on my projector in the back of the room, and then it'll always be there. It's nice and nice, a lot nicer looking than my sloppy handwriting, and it shows you exactly what to do. So keep that somewhere. Print it out. Put it next to you. Now, that being known, now we're going to go through the gauntlet of each type of problem and see how you do, starting with where we started off. Stone is thrown into a pool, not a pond now, but a pool, and it causes circular ripples. My pool looks just like my pond. As shown, the radius of the outer ripple is increasing at a rate of 1.5 feet per second. What is the radius of the ripple at 12 feet? And the total area of the disturbed water changing. Complete the question now. You're good, and you got an answer. See if you're right. Where we at? Circular ripples. Circle, circle, 2D figure, area, pi r squared. All right. The radius of the outer ripple is increasing. Great, increasing. Something over dt. What over dt? Radius, dr dt, equals 1.5 feet per second. The radius of the ripple at 12 feet, that's r equals 12. What? There's my find. Total area changing, something over dt. Total area, dA over dt. See that? You just figured it out. Starting to click. You didn't realize you were this good. Derive this equation in terms of t. dA dt, 2r dr dt times pi is pi 2r dr dt. Plug in our stuff. Don't know. 12, 1 1/2. 36 pi. 2 pi times 12 is 24, times 1 1/2 is 36 pi. All right, 36 pi feet per second, or if you want to make it a decimal, 113.1 feet per second. All right. We are? Awesome. All right, 15. Baseball diamond has the shape of a square with sides that are 90 feet long. The player running from second to third base at a speed of 25 feet per second is 20 feet from third base. At what rate is the player's distance S changing from home plate? Oh, I don't know what's going on here. Diamond, maybe diamond. Do we do area of diamond? It's a square. Oh, the area of a square. Sides are 90 feet. There's your player running. In case you don't know about baseball, you have to run around the bases. So if you're going from second to third, you're going here. You're going from home, that's his distance from home. That's his distance to third. So if I look at this, wait a second. All right, so I just connected the dots. All right, so I got home to third to player. That's no longer a square. What's that now? Now that's a triangle. A square. What do you know about a square? The corners of a square are all what? Right angles. So right triangle. Up. Ding, 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 ding. Not area, but it is Pythagorean theorem. Anything always the same in this Pythagorean theorem? The distance between the bases never changes. That's always 90. A, B, and then that's S. A squared plus 90 squared is S squared. A squared plus 8100 equals S squared. All right, so I got my equation. Drawing the diagram. All right, let's see what we got here. 20 feet from third base. So what's that? A. All right. 20 feet from third base. Running from second to third at a speed of 25 feet per second. That's d what dt? dA dt. Anything else we can find here? Oh, I can find S. I know this is 90. I know this is 20, so I can use... Oh, sorry. What is the player's distance S from home plate changing? So the distance from home plate changing isn't S, but it's what? ds dt. And then how can I find S? Pythagorean theorem. A squared, which is 20, plus 90 squared equals S squared. 400 plus 8100. 8500 is S squared. S is 92.2. So this is 92.2 feet. As we're on there. So when he's 20 feet from third base, which is actually be right about here, but that would squish my triangle. This is 92.2 feet. So a little farther than 90 feet. So catchers are actually doing this in the head when they're trying to throw people out. We're going to derive that equation. 2a dA dt, 0, 2s ds dt. A is 20, 25, 92.2 ds dt. 1,000 equals 184.4, 5.42 feet per second. That's how fast the distance from here to here is changing. So he's actually getting closer to home the farther he runs. Right? That's a little tricky. Problem 16. Construction worker. He's going to pull a 5-meter plank up the side of the building. So when he pulls the plank up, the plank goes like this. See that? If this was the plank, as he pulls the plank gets higher and it gets closer to the building until it's flat with the building, then maybe he pulls it up the building. So he pulls the 5-meter plank up the side of the building under construction by means of a rope tied to one end of the plank. Assuming the opposite end of the plank follows the plank perpendicular to the wall of the building and the worker pulls up the rope at a rate of 1.15 meters per second, how fast is the end of the plank sliding along the ground when it is 2.5 meters from the wall of the building? So, what figure is this? What do you think? Triangle. A squared, B squared, C squared. Oh, A is the bottom, B is the height, C is our 5 meters. So, we have a 5 meter plank, right? That's our C. A squared plus B squared is 25 is the formula that we're going to use. Let's look at some stuff. 2.5 meters from the wall. What's that, A or B? A. Worker pulls the rope at a rate of 1.5 meters per second. So if he pulls the rope, he's doing what? What is that? Is that dB dt or dA dt? dB dt, because he's pulling it up. So that's 0.15 meters per second. That's our dB dt. When A is 2.5, we could find out what B is, right? A squared plus B squared is C squared. 2.5 squared plus B squared is 5 squared, right? 6.25 subtracted from 25 is 18.75, and the square root of that is 4.33. So when A is 2.5, B is 4.33. Right? We good? And this is always 5. Whew. Now what? What are we finding? How fast is the end of the plank sliding along the ground? What's that? dA dt. Ready to derive? 2a dA dt, 2b dB dt, 0. Plug some stuff in. 2.5, we don't know. 4.33, 0.15. 5, 1.2999. Subtract the 1.3-ish from both sides. Divide by 5, and dA dt equals negative 0.26 meters per second. So this gets closer to the wall by about 1/4 meter per second. Right? And the negative just means your A is shrinking at 0.26. Right? That was an easy one, right? Hopefully, you pull out all your hair yet? All right, 17. Spherical balloon. This one's an easy one. Oh. All right. Spherical balloon inflated at a rate of 800 cubic centimeters per minute. So let's look. Spherical balloon. What's spherical? Like a globe, a sphere. What's the volume? So we need the volume of a sphere is 4/3 pi r squared. All right. So it's inflated. So we got a balloon here. All right. The volume is going in at 800 cubic centimeters a minute. So 800 cubic centimeters a minute. What have we got? How fast is the balloon increasing the instant the radius is 30 centimeters? So R equals 30. All right. What else we got here? Inflated at the rate of 800 centimeters per minute. That's dV dt. How fast is the radius increasing? Is what we're looking for. So that's dr dt. So what we're looking for is dr dt with a question mark. So if you ignore my last one, here's a nice little picture. I'll hold it up here for you. Maybe you guys can see it, maybe you can't. You got 800 centimeters blown into the balloon. The radius is currently 30. dr dt, it's expanding the more you blow in, and you're blowing in 800 centimeters per cubic centimeters a minute. All right? So, let us see. Derive dV dt equals 4/3 pi times 3 r squared dr dt. 4/3 of 3 is 4 pi r squared dr dt. We plug in our 800. We plug in our 30. 30 squared is 900 times 4 is 3600 pi. 800 divided by, open parentheses, 3600 pi, close parentheses. And you get 2/9 pi centimeters per minute, or 0.071 centimeters per minute. Right? That's pretty easy, isn't it? All right. 18. Oh, last problem. All edges of a cube are expanding at a rate of 6 centimeters per second. How fast is the volume changing when each edge is 2 centimeters? So first thing you got here is you have a cube, right? What do you know about a cube? Cube, all the sides are the same, right? So let me draw my cube here. There's my cube. All the sides are the same. The edges are expanding at a rate of 6 centimeters per second. So when the cube's rate expands, they're all expanding, right? So they're expanding left and right. They're expanding up and down. And they're expanding front and back, right? So you have all the sides expanding. So it's going out, it's going that way, and it's going that way. So how fast is the volume changing when each edge is 2 centimeters? So you want to know when each edge is 2 centimeters, 2, 2, 2, how fast is the dv dt expanding? Now, let's look. Equation. How fast is the volume changing? Volume of a cube is s cubed. Length times width times height, they're all s's. Given each edge is 2 centimeters, s's edge and side are the same, so s equals 2. All right. All edges expanding at the rate of 6 centimeters per second. S dt equals 6 centimeters per second. See? And all that helped that out was my little picture. All right. Find volume changing dv dt. Derive. Derivative of volume is dv dt equals 3 times s squared ds dt. Don't know what that is. S is 2. This is 6. 3 times 4 times 6 is 72. It's expanding at 72 cubic centimeters per second. It's because it's expanding in all different directions. It means it's really expanding. All right. Just think, the volume when this is 2, right, is 2 cubed, is 2 times 2 is 4 times 2 is 8. But say the volume after a second, it would be 8 times 8 times 8. So it would be 64 times 8, which is like, I don't know, like 500. It'd be a big number. All right? We all good? Yes? No? All right. Guess what? You'll be given these formulas, and that's the lesson. So now, you guys are hopefully better at related rates. You may not be experts, but hopefully you're actually comfortable doing the problems. And remember, the key to these problems is setting them up. If you can set up the problems, you can solve the problems. Deriving them is the easy part. You guys are great at deriving stuff. The key here is just setting it up. All right, so we'll review all this stuff. This is an implicit differentiation. Take a test on it, get A, and then you'll be set to move on to your quarterly, and then we'll move on to graphing, implicit differentiation, and we'll be good. All right, so till the next time I see you, take care.